Okay, I think I'm going to go ahead and get started. It is now 1:18. Yeah, so without further ado, the first example problem we're going to be doing today is problem 2.4. All right, so 2.4, we have the acceleration of a particle is given by a equals 2t minus 10, where a is in meters per second squared and t is in seconds. Determine the velocity and displacement as functions of time. The initial displacement at t equals 0 is position is -4 meters, and the initial velocity is 3 meters per second. So for this one, all we're going to do is start out just by writing down the basic equation that they give us, which is a equals 2t minus 10. And they ask for the velocity and displacement as functions of time. So a can also be written as a of t. So a is a function of time, and if you remember from our kinematics and also our relationships between the three different functions of time, all right, we have these guys. All right, so in order to get from a to v of t, we're going to have to take the integral of our acceleration. So without further ado, take the integral of 2t minus 10 dt. And that simply comes out, this is a basic integral, that comes out as 2t squared over 2 minus 10t equals v of t. All right, so there's that. And then it says the initial velocity is 3 meters per second. So in order to add that, you just go plus 3. Pretty simple stuff. If anybody was here, ask if they have questions. But so to continue on with this, now that we went from acceleration to velocity, now we can go from velocity to position, which is in their wording here, S sub O. And we're just going to write t here, just so we know it's a function of time. And now we're going to take the integral of the velocity formula we just obtained, which is 2t plus 3. And then all of that dt. And that is going to give us, these two's cancel by the way, this will give us t cubed divided by 3 minus 10 t squared over 2 plus 3t. And did they give us an initial position? Yep, they did. They gave us -4 meters. So we're going to do plus -4. All right. And that is basically it for this equation. And then, what else did they ask for? Oh, that's it. All right. So now we are going to move on to the next question. This is probably the easiest one we're going to be doing all day. So I hope nobody had questions about that. Give her one of these. And then go back in there. And then the next question we are going to be doing is 2-20. Okay, so a train which is traveling at 80 miles per hour applies its brake as it reaches point A and slows down with a constant deceleration. Its decreased velocity is observed to be 60 miles per hour as it passes a point 1/2 mile behind A. So the halfway point between A and B. A car moving at 50 miles per hour passes point B at the same instant that the train reaches point A. In an unwise effort to beat the train to the crossing, the driver steps on the gas. Calculate the constant acceleration, A, that the car must have in order to beat the train to the crossing by 4 seconds, and find the velocity V of the car as it reaches the crossing. All right. So what we're going to actually do is just take this diagram right here, pop it in here. All right, so we have the train at point A, 1 mile away from the intersection, with this car B at 1.3 miles away from the intersection. So we know both distances. That's important to know. So what we don't know, and what the problem asks for, is the time t for the first one. It also asks, or, well, we'll need it. It asks for the acceleration. It also asks for the final velocity of the train. So we have 3 unknowns there. So we're going to have to knock these out one by one. And then for the car, we have, they actually give us this one because they say it's 4 seconds before the train. So for our t here, we have t car equals t train minus 4 seconds. All right, so we have that. So what we're going to first do is we're going to start with the train and try to knock out these unknowns one by one. All right, so if you remember, one of the kinematic equations we have for this one, so it's going 80 miles per hour here, and in the problem statement, it says that it decreases to 60 miles per hour. So probably right about here, it's going 60 miles per hour. So we have an initial and final velocity, not the final velocity we're going to end up needing, but like the midsection one. So we're going to go with this kinematic equation. Sorry if this is sloppy. My real handwriting isn't that much better. All right, so now we have final velocity, which is 60. We're looking for the acceleration, by the way, because in the problem statement it said the train's deceleration is constant all the way through. So we got 60 here equals 80 here plus 2a s. And in the problem statement, it gave us s. Well, s is the position. So at this position, which is 0.5 miles, we'll just type that in there as 0.5. Okay, so now what we do is we're going to distribute this. We're going to do 3,600 minus 6,400 divided by this position of 0.5. Oh, and then it's also going to be divided by 2, which is going to cancel that out. So we're going to go there, that's just 1. And then we'll have this equals the acceleration. So our acceleration is negative 2,800 miles per hour squared. Okay, so now we can use that acceleration to find the ending velocity here at 1 mile. So now we are going to go with the same kinematic equation, but leaving this final velocity unknown. Okay, so our initial velocity is still 80. But now we have our acceleration as negative 2800. And then the position vector will now be 1. So, without further ado, we can go this way with it. Ooh, forgot the equals. 80 squared plus 2 times 2800. And then if you throw this all in a calculator, you should get V final is equal to 28.8 miles per hour. All right, so that's all well and good. So now we have the final velocity is 28.8 miles per hour. So what we're going to do here, get rid of this work, get rid of that little smudge, and then we're going to move this up here because we're going to need that. Yeah, so now to find the time that it's going to take for the train to reach the track here, we are going to need to use another kinematic equation. This one's a little bit simpler, which is t equals to the final velocity minus the initial velocity over the acceleration, which, if we plug everything in, we get t equals to 28.8 minus 80 divided by negative 2800, which will give us 0.0185 hours. So now that we have the time that it takes for train A to reach this intersection, we can take this, which is T train, and plug it into the T car in order to get the time it will take for the car to reach the tracks 4 seconds before this. So now, instead of T train, we're going to be finding T car, and that is equal to this 0.0185 minus that 4 seconds, but we're going to do 4 over 3600, just in order to convert it to hours to make everything easier. And then we are going to get the time for the car is equal to, if you plug both of those in, it's going to be equal to 0.01738. Fetty Wap's number. Okay, and then to continue on, we're going to go to the position kinematic equation. We're really hitting up all the kinematic equations in this example. So here we go. We got S equals VOT plus 1/2 AT squared, which we're going to start plugging into. So we have 1.3 miles, which is the position when it reaches this track. And then we got it equal to 50 times this time of the car, plus 1/2, and A's are unknown, and then the same T, oh boy, you get the idea, squared. Oh, actually I can just do this. Huh. That same t squared, which is 0.01738 squared. And if you rearrange everything, you're going to find out that A is equal to 2853.7 miles per hour squared. Okay. And then we're going to continue on with just one more thing. So now we have VF, which is our last thing that they asked for in the problem statement, equal to VO plus AT. Now if we plug in just one more time, you get 50 plus the acceleration we just found, multiplied by the time, which is 0.01738. And this should give us a V final of 99.8 miles per hour. Okay, that is all well and good. And move on to the next problem, which is going to be 2-23. All right, so this is actually a fun one. I like this one a lot, and it's not too bad. This is just to help you get X and Y axes, like movement on them, connected pretty much. I don't know what I'm saying. All right. So anyways, so this is 2-23. All right. So we got a toy helicopter flying in a straight line at a constant speed of 4.5 meters per second. All right, so it's this guy. He's going over here. If a projectile is launched vertically, right here, with an initial speed of v0 equals 28 meters per second, what horizontal distance should the helicopter be from the launch site S if the projectile is to be traveling downward? That's important. Hold on a second. That is important. When it strikes the helicopter, assume that the projectile travels only in the vertical direction. Okay, so in order to start this, you want to think, should I start with the helicopter or with the ball? Well, we have the most information about the ball because we have the height here. We have 20 meters, and the distance that this starts is completely reliant on when this ball is coming down. So we're going to want to find the time that it takes for the ball to come down and hit the plane. So we're going to start with the y direction, because when you have the most information about something, that's normally a good pointer. And also, this is completely dependent on when the ball is traveling downward. So in the y direction, we got y. Yeah, and then we're also going to label that the gravity is negative 9.8 meters per second squared, just so we all know. I'll put that over there. All right. Go back to this. All right. So ball traveling with only gravity acting on it is a pretty simple equation. We're going to start with y final equals y initial plus the v0 times t plus 1/2 a t squared. What I would recommend when you're doing these kind of problems is to have something like, I don't know if you're able to see it on my computer, but something like this up, just so you have all the kinematic equations like directly available to you, it's always super helpful. And like it'll give you a good sense of where you want to start and where you want to go. So anyways, we're going to start plugging stuff in. So y final, we're treating up as the positive direction. So y final will be 20 meters. Y initial will be at the base right here, which is 0, plus the initial velocity, which is stated to be 28 meters per second, and times the time, which is our unknown in this case, because we needed to figure out other things over here. And then plus 1/2 a, which is negative 9.8 meters per second squared, again, times the time squared. So you might be looking at this and you think, we have two unknowns. No, we really have one unknown in this one. And you're probably going to remember this right now, but we have the quadratic formula, which is negative b plus minus b squared minus 4ac over 2a. So we're going to have to rearrange this in order to get the a's and b's and the c's all in the right spot. So we're going to put this out front, which is going to be negative 4.9 t squared plus 28 t minus 20, all equal to 0. All right, so this is our A. This is our B. If you already know this part, you can skip it. This is our C. And then we're going to go negative 28 plus minus square root 28 squared minus 4ac, which is 4 times negative 4.9 times negative again 20. So these negatives are going to cancel. And then this will lead us to, oh wait, I forgot, all over 2 times negative 4.9. All right, scroll down. And then we got, once we simplify this, we get the negative 28 plus minus all this jumble in here is equal to 19.8 divided by negative 9.8. Oh, I forgot that. Keep it equal to 0. All right, so you got the positive and negative case, and then we're going to have here that this all equals to either 4.88 or 0.84. All right, so think for a second, which one of these are both seconds, by the way, because we are solving for t, which one of these would be on the way down? Well, don't think about it too long, because this initial one here, the 0.84, would be on the way up, just because it will keep traveling up and then come back down at the 4.88 seconds. And that is when it will be traveling downward and land on the helicopter. So don't be confused that there's 2 times here. It gives you which one you're going to need in order to solve this. All right, so now we have the times. Actually, I don't need to raise that. I'll just start something different. All right, so now we can finally use this time to solve for the helicopter starting distance, which is going to be d. All right, So next kinematic equation is also very straightforward. D equals x naught plus v t. And it already gives us the v. It doesn't give us the d, and we just solved for the t. X naught, if we state that this place is actually going to be 0, to start off, we get d is equal to v, which is 4.5, times time we just got, which is 4.88. And this gives us d is equal to 21.9 meters. Okay, so this is the third example problem that we're going to be doing today. The next one is a little bit trickier. Again, this is just to get you going on those up and down problems, get you in the right mindset with like where to start, when to find t, which variables you're going to need first, and then consequently which ones you'll need second. All right, geez. So without further ado, let's move on to the next problem, which is going to be 233, which is actually a pretty fun one. So I'm guessing, I took this course second semester of sophomore year, so I'm guessing that's where pretty much all of you guys are. So I'm assuming that you've all taken Calcs 1, 2, and possibly 3. I forget, it's been a time. All right, so got 233 here, and we don't really need that. All right, so we got this guy, which is a projectile, which we will model as a little blob here, goes downward at 4 meters per second. At 4 meters per second. And goes into an experimental fluid. So this is the y-axis right here, going downward. So they give us this projectile is fired downward with initial speed VO in an experimental fluid with experiences an acceleration A equals sigma minus n velocity squared, where sigma and n are positive constants and v is the projectile speed. Determine the distance traveled by the projectile. All right, so we're going to need a s variable at some point. By the projectile when its speed has been reduced to 1/2 of the initial speed, VO. Okay, so we have two conditions. So we have VO, which is 4 meters per second, and 1/2 VO, which will be 2 meters per second, which we won't really need to use these until the very end. All right, so we're going to start with the knowledge that the acceleration is equal to v dv over dy in this downward slope. Okay. So then we're going to use this because we can't really do much with an acceleration because we don't have any givens about its acceleration other than the things needed to solve for it. So we're going to switch this to velocity and then plug that back into this equation. So now we have v dv over dy equal to sigma minus n v squared. I should know what that n stands for. Ugh. All right. And then if you remember from calc, I think it's calc 1, maybe? I don't really know. We have the separation of variables. So we have a v over here, got a couple of v terms over here, and we have a y. So we want to relate the velocity only to the displacement. So we have the y here, and through separation of variables, we can change this to this v dv over sigma times nv squared equal to the differential relating to y. Okay, so then if you remember following the steps of separations of variables, obviously this looks like something you just like can't pass up the opportunity to take an integral of. So we're going to throw one of these over here, one of these over here, and this is just displacement, so we're going to just like mark it 0 to y. Well, this one's a little different because we have this velocity term, and we are given the condition that we want to start at v naught and end at when it is half of v naught. So we're going to give it 1/2 v naught. Okay, so this might look a little intimidating. Don't get scared of it. It's just a couple of constants as they give us up here. They give us the 0.7, the 0.2, and the 4. So don't worry about any of these. They'll go away. But that being said, we have a v term up here and a v squared term down here, and dv, which it might help if I throw this dv, find it, just so that we know that it's not in the top term. But anyways, this one's easy. The integral of dy from 0 to y is just y minus 0. That's simple. So now we have to really focus on this one. So the integral from VO to half of VO, V over this stuff, and this should give you a clue. So when you have a v squared term under a v, automatically think, oh, that could be a natural log integral, right? So you flip open your table of integrals, and you're looking through, and you can't find anything that looks like this with a v squared, two different constants, v on top, and you just don't know what to do. And then you think, oh, what did I learn? So when you really don't know what to do, the first thing that you should always try is the U substitution method. So if you take, because you know that this differential, if you take the differential of the bottom, you're going to get a bunch of constants multiplied by the term on the top, and also this term right, the differential in relation to the term on top. So using U substitution, we want to say that U is equal to sigma minus n v squared, and then if we take the differential in relation to u here, yeah, so we get, yeah, so if we do du dv, oh boy, that looks too similar. That's the u right up there on top. But anyways, I digress. And then that will be equal to, so this is a constant, so it's just going to go away. 0 minus, and then we're taking in relation to the v term, so we're going to have to take this 2, pull it down here, so minus 2n times velocity. And yeah, and that's it. So then we get that this du term is equal to negative 2 and v dv. All right, so now we got all the stuff we need. Man, this is too cluttered. Pull this up here. All right, so now we got all the stuff we need in order to plug this back into this equation. So we're just going to go for it. So we have the integral. This v stays on top over, and then u. Oh yeah, we're going to sub in the dv term, which if we go over here, we have it equal to du over negative 2n v dv equals du. Yeah. All right, hold on one second. Move this up. Oh god. Move that up right there, just so we know. So we're going to plug in this term, which is going to give us that v up on top multiplied by this negative 1 over 2n v, and then all that multiplied by dv. Okay, and then these v's are going to cancel, and you'll notice that now we just have this negative 1 over 2n all multiplied by this u and dv. So since these are all constants, we can just pull them out of the integral, get them out of there. So we have negative 1 over 2n is equal to the integral of 1 over u from VO, let's put them over here, 0.5 VO. Yikes, this is a mess. I'm going to rewrite this. Yeah, so dV equals negative 1 to n v du. Okay, so that's what we plugged in over here. Okay, and then we get to this point. Now I have the negative 1 over 2n, the 1 over u du. There, now we can take a good looking integral. Okay, so now we have this one, which hopefully you guys can see that it will just go straight to the natural log function of u from VO to 1/2 VO. All right, so we're getting close. Let me get rid of all of this clutter. If you need to go back, just rewind. Boy. Keep that. Okay, just leave it there. And then really go for it over here. Oh boy. All right, so now we have this term. -1. And if you remember, we're going to resubstitute in what we took out for the u now. So, and put it from 1/2 v. We'll wait on that. We'll do two different steps. So we have -1 to n ln of the u term, which when we took it out, we made it equal to sigma minus n v squared. And that is all from v naught to 1/2 v naught. Okay, so now we got this. We're getting very, very close. So now we're going to substitute it in. We have -1 over 2n ln of, and since we took the integral with respect to v, we're going to plug these in for the v's. So we got sigma minus n v, and since it's v squared, v squared times 1/2 squared minus ln of sigma minus n, and then this is the second term, so it's going to be the v naught here. V naught squared. And then if you remember the principle of logarithms that have the same base, these are both base e, so we can just merge them. And when you subtract two logarithms with the same base, you can take one logarithm with the first one in the numerator. And the second one in the denominator. Oh boy, this is getting messy. And now we get to look forward to plugging all of the variables they gave us in. And this has all been equal to y ben, by the way. I totally forgot to include that. All right, so now we have y equal to -1 divided by 2. And we're going to plug in that 0.2. And then ln of this whole mess, oh boy, which is going to be 0.7 minus 0.2 Sorry, I'm just looking at all the variables. And if I'm plugging anything in wrong, correct me. And then, if you plug all of this into your calculator, you are going to get that this y value is equal to 8.05 meters, which is quite a lot of fluid actually, if you consider what that diagram looked like. So, yeah. And then it also asked the question, what is the V terminal? So for V terminal, This is pretty simple. Wow, look at this rating. It'll be equal to 0 equals and then if we set this, since you see it's 0 right there, then we can rearrange all of this and put this on that side, divide it by the n, and then take the square root of it. So this would be negative and this would be negative, but that just cancels. So we're just gonna ride with this, and then this is just 0.7 over 0.2 under square root bar, and then we get V terminal is equal to 1.87 meters per second. And that is it. I'm going to probably stop recording, but if anybody shows up and has questions, I will be here until 2:45. Yeah, thanks for watching.